In this video, we are going to continue our discussion of section 4.1, preliminary theory for higher order linear differential equations. What we're going to do right now is just kind of apply the two ideas. We read this theorem, and I did it pretty quick because I know when we read theorems, you should slow down and read them. But I kind of think at this level, you should go forward, do an example, and then I want you to go back and read the theorem to make sense out of it. I think that'll help with a total understanding. That way you can apply it to different problems. All right, it says verify the given functions form a fundamental set of solutions of the DE. Okay, so remember that if our solutions, right, the set of solutions are linearly, right, if they are linearly independent, set of solutions are linearly dependent if the Wronskian of our F1, F2 in this case does not equal 0. That implies the solutions, the set of solutions form a fundamental set. Form a fundamental set. Remember, this means that all solutions to that equation, fundamental set of solutions. I guess we could have said are fundamental. So what this means is that if those are fundamental, if the two solutions that were given, if those are fundamental set of solutions, then I can find every solution to that diffie through the general solution, which is the linear combination of the two given. So first things first is I have to find the Wronskian of F1, F2. And this is only a 2 by 2, so it's pretty quick, a lot quicker than the last video. We have cosh, so hyperbolic cosine. Hyperbolic sine. Remember, these are just, it's trig on a different plane, right? It's just not in nice, pretty 3D world. And it's still 3D, but not the same surface. Okay, cosh of 2x. Remember, this is chain rule, so 2 comes out. And hyperbolic cosine just gets me hyperbolic sine. Same thing with the sine. I get the 2, and then it becomes hyperbolic cosine of 2x. That's it on this one. There's no third because I need to make a square. So I guess I could have made these shorter. Right, so we have that and that. Okay, and then I know that to do these, it would be like we're already to the end part, like we did a second ago. It's this times minus those times. So we get, I'm just going to go down. Okay, I get 2 cosh, and then it's squared 2x minus 2 sinh squared 2x. Right, be careful. You see that sine squared, cosine squared. But like these are hyperbolic. It's different. So I see a 2, so I'm going to go ahead and factor that out. Right, and we're not going to prove this. This isn't something I would put on an exam because I don't know if your Calc 2 teacher did much of hyperbolic sines and cosines. But here in hyperbolic land, that actually is the Pythagorean triple. That gives me a 1. You're not going to be held to that, right? That's what I just said. I'm not going to ask that on an assessment, but it's a good thing to be familiar that it's different. Okay, so this means this is not 0, and that proves that they are linearly independent. And then since they are linearly independent, that tells me that they are the fundamental set of solutions. And then they asked us to form the general solution. So y equals, we just put a constant, cosh 2x plus c2 sinh or hyperbolic sine 2x. So there is our solution. I'll usually do green or do orange. All right, so it's pretty nice. As soon as you can show that they are linearly independent, you have actually grabbed a general solution for that homogeneous equation or homogeneous equation. All right, we're going to do another example like this. And then there is a new theory that we can piggyback off of this of. All right, so verify that the general functions form a fundamental set of solutions of the DE on the indicated interval and then form the general solution. So same idea. That okay, we have first, I guess we should probably guarantee because we need to be able to see these. That's a second order linear. We have to make sure that it is linear, and then we have to make sure that it is a fundamental set before we grab a general. Okay, so I know that I got to go to the Wronskian. They didn't give me F1, F2, so I'm going to actually write this. I know I didn't do that the last time, but I can do it here. We could write it like this as well. All right, and then we know this is just a 2 by 2. So I get cosine of ln of x, right? And then we got to be careful. This is going to be a chain rule. I'm going to get cosine is a negative sine of ln of x. And then the derivative of ln of x is 1 over x. So I'm going to get negative 1 over x sine ln of x. The sine came from the cosine, right? I keep the ln, it's a chain rule. Derivative of, and I get the negative from that as well. Derivative of ln of x is 1 over x. Okay, then we're going to do the same thing for sine. Derivative of sine, this is going to work out the same way without the negative. All right, and then this is our normal determinant, just a 2 by 2. So I'm going to get 1 over x cosine squared ln of x. You still square it, doesn't matter that the ln's on the inside. And then it's minus the product of the other, this diagonal. Sorry, this diagonal. So minus is going to cause a plus, and then I'm going to get sine squared ln of x, right? I have a 1 over x in each one. So I got 1 over x times cosine squared ln of x plus sine squared ln of x. The Pythagorean identity applies as long as the arguments are the same. What I mean by arguments are what's inside. If that was an x and a y, that wouldn't work. But since they are both the exact same thing, we get a 1 every time, as long as that's the same thing. Well, this is not 0. That implies that they are linearly independent. And then that implies that it is a fundamental set. Right? And then I can grab my general solution. Y equals C1 cosine of ln of x plus C2 sine of ln of x. Before we move on, there's our solution. I want to point out just something I'm going to emphasize because we're about to kind of change gears a little bit. And I don't know if we've been putting, I can't highlight, I guess. I haven't been putting, I think, enough emphasis in the videos thus far. So I want to make sure that you are catching that this has to be homogeneous, has to be, right, to do this theorem. We are going to work with this. We're going to take, if it's a homogeneous, then we're going to change it to homogeneous and find it using this method. So you need to know that this Wronskian method to get to a general set of solutions only works, the way we're doing it right now, only works if it's homogeneous. Okay. Otherwise, you cannot use it, right? If there's something on other than 0 right there where I've highlighted, we cannot use this. There's another theory that I'm about to introduce, another theorem, I mean, that will help us find the solution to a non-homogeneous diffie. That's probably going to be, that's going to be what we're moving forward from is what do we start putting over there on the right? And how does it change the methods? All right. Have a good one.